Oh, hush. Oh, hush back there.
My mom always felt that sleep was the most important thing, so she was happy that she made that decision.
It gets to a point where I have to have some of it.
It was 2 years ago, I had a student who had to have her 12 hours of sleep every night.
Well,
I was thinking, geez, I'm not sure I've ever had 12 hours of sleep.
I would be fine with 6. That's about what I'm getting. Yeah. I don't think I've ever got 12 hours.
How's that even possible?
I don't even get home early enough to get 12 hours of sleep. I got home at 11:40 last night from UPS.
My wife grew up on a farm, so she said homework she could not even begin her homework till 10 o'clock at night.
Yep.
I understand.
Understand you.
My degree is in equine science. So,
Ah, okay.
yeah.
All right, so the work energy was 7, that was 8. And this should be 9. All right, so let's start a little bit about chapter 9. We're basically going to double the number of equations we've dealt with in about 10 minutes, within about 10 minutes.
Yay!
That's right.
Let's rejoice.
After all, it is physics.
Start straight. So we've been doing a lot of linear stuff. The only curvature that we've really done of any note has been circular motion, centripetal motion. But whenever we've done centripetal motion, we've kept it so that the speed was constant. So now we're going to add to that. So the linear or translational quantities is what we've primarily dealt with. And for each of these linear translational quantities, there's a rotational or angular analogy. So we'll list down the things that we've done and then talk about sort of the rotational. Equivalent is really not the right word, but equivalent anyway. I feel like muffled more than usual. I guess if more and more people hear about the fact that we're doing physics, they just come right in.
Just can't keep them away.
I know.
Is there already
Pardon?
is there already a stack board?
As soon as you put it down, there's a stack. All right.
Yes, sir.
Now, for those of you who are not ready with it, you can thank Kano for handing it in, because if no one hands it in, I've immediately graded all the ones handed it in on time. So the
He
fact that
could
it's handed-
pick it back up. I mean.
No, if he picks it back up, it hurts everybody.
Oh, okay.
So you need at least one person to hand it in on time.
Okay.
And that's just it, so.
So even though they have not expressed it, they say thank you to you.
Yes, thank you.
Thank you.
You're welcome.
You're awesome.
You're responsible.
You too.
All right. So position is the linear quantity that we've dealt with here. Typically I use X, but it could be Y, Z, R, S. These are all the letters that I've used at various points in my lifetime for position. And then over here we have our rotational analog. And the rotational analog of, or analogy of position is angle. We have dealt with displacement for a few months here. And it's just delta S, etc. It's the capital delta in front of whatever letter we're using for position. And the rotational analog is technically angular displacement. Although oftentimes the wording is angle. Just as position and displacement sometimes are used interchangeably. I try to distinguish between the two. I'm a little less careful with angle and angular displacement. So I have something that's rotating, I have a wheel that's spinning. I might just ask, through what angle is it, in the first 2 seconds, through what angle does it rotate? And what I'm really asking is, what is the angular displacement for those 2 seconds? Oh. All right, so linear and translational can be used interchangeably. I tend to use the word linear, but as you get into more higher levels of physics, translational tends to be the term that's used more. Over here for rotational and angular, they are used interchangeably, but tradition has usually one word or one word is used. You tend to talk about angular velocity, not rotational velocity. But if someone talks about rotational velocity, it means the same thing. The symbol for angle, typically it's a Greek letter. Theta is what I use usually as my default, but it could be phi or a whole slew of things. And angular displacement is just the delta in front of whatever you're using for angle. Velocity, V with a vector symbol. Angular velocity. They really got clever with the names here. And the symbol, there's a U there. The symbol is an lowercase omega. Lowercase omega. Uppercase omega looks like a horseshoe with all the love running out. Acceleration, A. Someone want to take a wild guess at what the analog is?
Angular acceleration.
Right on. And the symbol, still keeping in that theme of, let's use Greek letters for rotational things. The general thinking is acceleration starts with an A, alpha starts with an A. Hey, let's use alpha. Or some students have called it the Jesus fish, but it's alpha. All right, so I haven't really defined what they are yet. I'm just presenting vocabulary words right now. Any questions at the moment? All right, there's going to be a longer list, but for right now, let's just talk about the equations. Why I said we're going to double the number of equations. So let's take one of our cake formulas. Delta S is equal to VIT plus 1/2 alpha t squared. I guess we need to talk about time. Let me throw time in before we get to that. The angular analogy of time is time.
Time.
Yeah. The time it takes for something to rotate, the time it takes for something to move from a particular direction, it's the same time. All right. So to come up with a new formula here for the rotational stuff, wow, no one called for that. It's an A there. Is you just transliterate. So instead of an S, we use theta. Instead of V, we use omega. t time plus 1/2, there comes the alpha, t squared. And so we have a rotational or angular cake formula. So as long as angular acceleration is constant, this is a valid equation. So we have Vf squared equals Vi squared plus 2a dot delta S. So we want to take a shot at the rotational equivalent or analogy.
Omega I squared plus 2 alpha, is that times,
Yeah, that specifically is a dot product, so it should be dot.
delta omega, no, theta.
Yep. A little sloppy there, should be a vector symbol over those. This is a lower case theta. All right, so we can take all those equations, all the equations from chapter 2 and chapter 3, and boom, we've got a new equation. Let's hit a couple more linear things that we've done, because then we get into chapter 4 where we start talking about forces. And so let's first start out with the force. It is not called angular force or rotational force. This is where torque comes in. And the symbol is a tau. Pretty sure it's lowercase. So a force is an influence which might cause an acceleration. Torque is an influence which might cause angular acceleration. A force is a push or pull. A torque is a twist. In a sense. Mass. Now there's still mass when things are rotating, however, there is an analog of it, so mass is m. The analog of it has two different names, and I will flip back and forth between the two different names. The two names here are moment of inertia, which I probably use more than the other one, but I do flip. Moment of inertia, or rotational inertia. Moment of inertia is probably a better term for it. Because inertia itself is not a quantity. Mass is the quantification of inertia. In other words, the greater the mass, the greater the inertia. But calling something rotational inertia, to me, implies inertia as a quantity, and it's not really. The symbol for it, and this is the first one, I guess, where we don't use the Greek letter, is a capital I. So we can now take our Newton's second law, F equals ma. So we want to take a shot at what the rotational version is.
Tau equals I alpha.
There we go. brand new equation. And I did not give myself enough space there, so I'm gonna squeeze it in up here. Linear momentum. So it's P with a vector record. Momentum. Angular momentum. And again, for some reason, they decided not to go with a Greek letter, and they basically, it's a capital L with a vector symbol. So I know that P is equal to mv, L equals
Omega.
Omega.
What I forgot, I think that pretty much covers it all. That goes right there. FMP. Let's do one other transliteration of a formula. A equals 1/2 mv squared. The rotational kinetic energy equals what? Yep, there you go. Now, when we first did kinetic energy, and I had you repeat in unison the formula for kinetic energy, and I said, the reason why this one is was in any of the others, or if I didn't, I meant to say it. The reason why I wanted this one memorized is that the formula for kinetic energy is 1/2 mv squared. You're working on your Nobel Prize winning work, that's the formula. All the others have a slight variation that kicks in once you start getting to extreme values. And here I am introducing another kinetic energy. Have I contradicted myself? I have not, actually. But how we get from here to here, why this is not a different formula, we will get to. Because in doing so, we'll explain exactly what I is, besides moment of inertia. There's one other eccentricity that I do want to bring in, just because I'm trying to keep this alive. Probably there are very few people in this country who will understand this reference, well, actually the world, and I'm not going to explain it. But torque, in my class, you can, instead of saying torque, and it's not necessarily more convenient to do so, but you can also call it G2 Kumbuka. I think it's hyphenate there.
How do you pronounce it?
I pronounce it G2 Kumbuka.
That's something we need to know.
I think it's good to know this guy's name.
Okay.
I will say that I consider this to be my most obscure reference. This was obscure in the 90s. It's even more obscure now. I did have a student who knew the reference because of something his father had told him. I don't know which was more shocking, the fact that he listened to his dad or the fact that he remembered the reference. But I will leave it unexplained, and you can find out on your own if you wish. Not now, though. All right, so let's use some of this newfound stuff. I think that's the technical term for it. 30 meters per second. Accelerates uniformly at -5 meters per second squared. At what point is it going at positive 30? Is it going -10 meters per second? All right, the chapter 2 type problem right there. So we set up just like we've done before. I have displacement, initial velocity, final velocity, acceleration, and time. So what do we know?
We know initial velocity is 30 meters per second.
Okay.
Yeah, is that accelerates uniformly at -5? Is that what you have?
So,
I was asking, is it -5 you have for?
yeah, that's -5. But that also identifies something else we know, -5 meters per second squared. And we got one other piece of information.
Final velocity at 10 meters per second.
Negative.
Thank you.
Yeah, I thought I said it. Oh.
I didn't hear the negative, so.
I
It's a
don't
team
remember
effort.
if I said it.
Team effort right now. All right, so how do we find, at what point, I'm at time? So how do we find time? Since acceleration is uniform, we take formulas, which formula is the simplest?
The acceleration formula.
Okay. Which in cake form is VF equals VI plus AT. So we have -10 is equal to 30 plus -5t equals 8 seconds. Just straight up plug and chug. So let's make this more about chapter 9. A wheel is initially rotating at positive 30 radians per second. It accelerates uniformly at -5 radians per second squared. At what time is the wheel rotating at -10 radians per second? So we have our 5 quantities. We have angular displacement, we have initial angular velocity, final angular velocity, acceleration, and time. And what do we know?
Initial angular velocity is 30 radians per second.
Okay. say them out.
Acceleration would be negative 5 radians per second squared.
Yep. You know, one other thing.
Oh, where the final angular velocity would be negative 10 radians per second.
Yep. So which formula are we gonna use?
Same one.
Yeah, except for the rotational version of it. So we have omega final squared, not squared, wrong problem. Omega final equals omega initial plus alpha t. And then it looks exactly like the other problem. So if acceleration is constant, it's the same type of stuff that we did in January. Questions?
Doesn't your A need to be alpha on the
Oh,
second side there?
yes, thank you. All right, so the next question, so I'm just sort of piggybacking on stuff that we've already done there, so I wasn't gonna go into a lot more detail because there's no real angular projectile version of it, so it's just all similar to one-dimensional. Oh, something else I need to do though. What does positive 30 radians per second actually mean, or negative 10 radians per second, other than one is one way and the other one's the other way? I just happen to have a wheel right here. How would you describe its angular velocity? Pardon? Well, probably a lot more constant than a lot of the other things. It's slowing down a little bit. Let's try this differently. So 1001, 1002. All right, so that's about 2 seconds to go all the way around. So that's about a little more than 3 radians per second. But that's the angular speed. What's the angular velocity? What's the difference between speed and velocity?
Direction.
Okay, so how would you describe the direction of the wheel spinning?
Clockwise.
I would have said counterclockwise, but
Pi,
pi?
yes, because it's going in a circle.
Yeah.
Positive. Based on the sticky note on it.
Maybe someone was backwards. They're just messing with Brandon. Oh, I guess that doesn't, I guess that would make it negative, just go with the sticky note. All right. But what Amy said clockwise makes sense. I assume all of you, I think even Kano, I think you're at the steepest angle here, but all of you would sort of agree clockwise.
Yeah.
But from my point of view, it's going counterclockwise. So how do you resolve that? Or do you have to describe it, well, the wheel is spinning clockwise, but if you're standing in the main part of the room and it's being spun near the board, that's a lot of words. And I guess you could do that, but surely there's a simpler way. How do you come up with a system that works no matter where you're standing?
bird's eye view.
How would you describe that then with a bird's eye view?
Like as long as everyone can look at the object from above it, such as the wheel. Like if the wheel was on the ground, then everyone would have the same.
Yeah, but I could also then do this, and now you're left with the same problem that you had before. What the powers that be came up with was a right-hand rule. There are a lot of right-hand rules in physics. This is one of them. It is not the dominant hand rule, it is the right-hand rule. Your thumb is the axis. So if I'm spinning it like this, that axis is either pointing towards the back of the room or the front of the room. So my thumb's either gonna be pointing that way or that way. My fingers need to curl in the direction that it's spinning about the axis. So if that's the axis and I'm spinning it like that, then my hand would go around like this. My thumb points in the direction of the angular velocity. This is a notation. This is, if I said that the angular velocity of this wheel was towards the front of the room, then anyone who understands this convention would know, oh, it must be spinning around like that. You don't need to describe where you are in the room. It's not dealing with the clockwise, counterclockwise, which is a perspective thing. So if I spin it like this, the angular velocity is towards the ceiling. Because my thumb is either up or down, but it's spinning around like that, it's up. So we've gotten away with I and J in the past, but now we have to bring in K. I don't think we've dealt with cross products. Other than I mentioned them briefly, but I don't think we went into cross products. First off, this is the left-handed coordinate system.
Should be a plus right there. X, yeah.
Plus or X. Someone indicating it's going into the board.
Looking at the feathers. Looking at the feathers.
Yep, absolutely. Do you know why